All right, folks, let's start. This is Dr. Yuzo. It's ECE 360 control system class. Can you hear me? And also being able to see my shared screen here. All right, thank you. Thank you, folks. Thank you, folks, for letting me know. Good. All right, so midterm was on Monday, and haven't got any time to grade yet. So we will see the results and solutions maybe next Monday, or maybe even next Wednesday. Okay. This is the intro, and so we're here. We're at this particular cell, the first lecture of new module 4 time bonds. Okay. And time response. Okay, is to understand what we are talking about. We need to go back to the very first lecture in where we present a kind of summary, or say the correlation among those modules, among all of the modules we can learn, right? So we have done module 2, frequency domain modeling, module 3, the transfer function block diagram. After understanding these two modules, we go ahead to do module 4, which is the time response. So time response, this module is for what? As saying here, module 4 is trying to answer a question. How do the system input and output look like? Okay, we are talking about signals. Okay. How to figure out the input and output signals? Well, the input is given. Okay. It is given. Okay. It's a particular input. We will see what kind of input signals we're going to use. And we are mainly studying the output. Okay. Output, if you go back to the this generic block diagram, which is also one of our, not one, but I think three multiple choice problems in the exam 1. Okay. In this generic block diagram, output is here, right? It's output, a signal. There's output signal here. So we are studying this guy. Okay, we are studying this guy, output, based on one particular given input, and of course, as well as the system transfer function like this. Okay, we are studying the output. What does it look like? What does it look like? What in time domain? Okay, in time domain. All right. How to do that? We are using the system transfer function and the input, two things determining the output. All right, now remember two things. One is input, another is system transfer function. Two things determine the output. All right, and in the output we will see once again in time domain. Okay, we see transient and steady state, etc., etc. So-called performance. So-called performance. So what we are studying the transient and steady state and other specifications for. Evaluating the performance of the system, right? You're checking output, however, you're evaluating the performance of the system. Does this make sense? So this is the overall picture, or say the idea about this module, Okay. So with these being said, let's go ahead to see the notes. As usual, we just write our notes under doc count. Module 4, time response. All right. First of all, we need to clarify some concepts, basic concepts. Some of them you know, some of them probably a little bit blurred. So what this module is doing, analyze the system output in time domain using what? Frequency domain transfer function. And being clear, okay, the system output, who is the output? The output is nothing but, we call it response, okay, response. Okay, we call it response, okay. Output is nothing but response. And basically, what we are doing is, first of all, a system which has the system transfer function g of s. And of course, we have an input. If you recall, we using the R to represent input, C as the output. So this module is obviously studying this guy. What this guy is. What this guy is. And what we do is, based on this transfer function, we are trying to come up with this. Here, in time domain, okay, this is the time domain. We just mentioned, we are trying to figure out the relationship, or say, between this time domain waveform, or say the curve, the result curve of the output. So it's not C of S anymore. This is C of T, right? Lowercase c of T. Does it make sense? So what does output versus time look like, right? Of course, by the way, from this capital C, or from this block diagram, capital C of S, we got lowercase c of T. Anyone remember what we did? How to get this lowercase c of T? Very straightforward. What we do? From here to here. We're applying whatever we have learned in previous.
Is it inverse Laplace?
Very good. Nothing but inverse Laplace. Nothing but inverse Laplace, which is one of our midterm problem as well. Partial fraction, right? Partial fraction is considered as a part of the inverse Laplace transform, because before applying the Laplace transform, you need to do the partial fraction, right? Good. This is one of the idea, one of the concept here. And then second, system output is a sum of forced response and natural response. If you have ever learned these two terms before in differential equation, it wouldn't be a surprise to me, okay? Because these two terms is also the solution for a differential equation. Okay. So a sum of forced response and natural response. However, in control system, in this subject, in this class, we're not mentioning the forced and natural response. Instead, we are mentioning what? Forced response is what? Nothing but steady state. Okay. Steady state result. Steady state response. Or say SS. Okay. The natural one is what? Transient. Is the transient. Okay. Because we are mentioning these two terms instead of natural or forced response. So this is the second one. So once again, this is output, nothing but a response. Okay. The system response means nothing but system output. Okay, output. Next. Output, or say response. Never forget this. Okay? Never forget the basic, very basic definition of the transfer function. So your output over the input equals to the transfer function, G. Okay. Always never forget this very basic definition. Very basic definition. Based on which you can derive the what? Derive the numerator, which is the output. Okay. This is the very basic definition we are based on to find out to derive the output. As I said, what do you see? Output just equals input times the system transfer function, right? It's very straightforward, very straightforward. And from here, what we can do? Like Sawyer mentioned, we apply the inverse Laplace transform. You got lowercase c of t, which means you're gonna do this, right? Inverse Laplace transform onto the product between G and R. Does it make sense? And then what do you do? Partial fraction. And then what do you do? From there, you check what? Tables, right? And then you got the time domain. Up, right? Does this procedure make sense? We're gonna have, of course, much more specific examples, but the rough idea is not difficult to guess. Okay, the rough idea is not difficult to guess. And here is also verifying one idea I just mentioned. So the system output is up to two things. Okay, two things. Not only system transfer function, but also a particular input. It's absolutely matter. Okay. So system performance is up to the system transfer function and the system transfer function only. However, the system output is up to two things: system transfer function and a particular input. Okay. And then we talk about a little bit input. Very easy, very easy. What input? For inputs, actually, you want to go back to the handout, the Laplace transfer table handout. And specifically, let me find it out. And this is what I'm talking about. This is what I'm talking about. This is the handout from previous module, right? And from this module, we introduced the 4 signals with names of impulse, step, ramp, and parabolic. Okay, so our input signals used in this course is just one of them. Okay, just one of them. Okay. And the most of the time, I give it here. Perfect. Okay. And the most of the time, impulse, step, ramp, and the parabolic. Most of the time, we are using the second one, the step. Okay, you just use the step. You just use the step. And from this table, we can also tell the time domain step signal looks like what? A constant, right? Time domain, what does it look like? Zero, when t is less than 0. A constant value, say a, when t is equals to and greater than 0, right? This is step, this step signal. One of our midterm 1 multiple choice, right? And this step. Okay. And the corresponding frequency domain S function is what? It's constant A over S. Right? Constant A over S. Okay. So we're gonna use step a lot most of the time. However, keep in mind that we also have 3 other options: impulse, ramp, or parabolic. Okay. All of them matter. All of them matter. Do matter. Okay. So from this table, you can find the time domain expression as well as the corresponding S domain expression. Okay. This is the input signal, based on which we're going to study the output. Any questions so far? Any questions?
What kind of sources would have a parabolic motion to it? Like, I understand if you're turning a transistor on, it'd be like a step or maybe a ramp. But
Yes.
what would actually have a parabolic shape?
Well, that's very special. It's very special. First of all, what kind of your idea is like this, that the step is very commonly used. It's just a constant, give certain fixed number, constant value, right, without any change in observing the system performance and output. However, sometimes if you want to check more dynamics, you probably want to introduce like a ramp or even parabolic. The ramp is what? The ramp is something that input signal is very linearly with a constant slope, or say with a constant first order derivative value. Right? This is a type of input. Parabolic is what? Constant second order derivative. You know what I mean? So constant, and then to first order derivative constants, and then go up to second order derivative constant. Okay, so this is pretty much a differential equation idea. Increase the level of derivative order to observe the system behavior. And what kind of source can give you that? Well, it's actually quite rare. It's quite rare. Maybe some, it's very special. You give a changing acceleration. You know what I mean? Ramp is constant acceleration, right? You're increasing the acceleration, increasing the acceleration. That is nothing but the parabolic. You know what I mean? A constant speed, as I was saying, just a motor. You gave a constant speed, okay, that's the step. You gave a constant acceleration, okay, that's a ramp. You gave a increasing acceleration, which is possible, of course possible, second order, right? And then of course that's parabolic. It's for testing the system performance, quite dynamic, very aggressive. Your acceleration is even changing. The acceleration is even increasing, right? Does it make some sense?
Yeah, I could see that.
All right, good. Now let's study the specific system. That's the specific system. The first one is first order system. It's easiest one. First order system. Give you an example like this. With constant k and a, you have a transfer function like this. The system is called first order system. Of course. What does it mean by first order system? Or say, what does it mean by system order? Anyone knows what does it mean by system order? How can you tell this is first order system? by watching the by seeing this transfer function. How can you tell this is first order?
Because the s, there's only one present in the denominator.
And that's right. So basically, this order, system order, means the order of S polynomial in system transfer function denominator. So in this case, obviously, denominator is first order equation, a first order polynomial, so of S. So it's first order system. But be very, very careful. Okay, be very, very careful. One popular mistake is happening here. We are looking at the S polynomial order in the denominator of system transfer function rather than output C of S. Okay, be very careful. Okay, this is a very popular mistake. We are checking the order of system transfer function rather than the output signal. Okay. Right, and then let's check the unit step response. First of all, what does it mean by unit step response of this first order system? What does it mean by unit step response? Anyone understand?
Is that if RS has a unit step function incorporated to it, or?
And then, yeah, basically, John is right. And what does it mean by unit step response? Means the system output when applying a unit step input okay, this is the correct understanding. Not difficult, but so unit step means what? The input. Response means the introduced output. Okay. Now let's see the unit step response of this guy. Given the system transfer function, we should be able to find the output, right? So first of all, what does it mean by unit step input? What is it? In S domain, of course, we are using the S domain. R of S equals
a constant over S.
Constant is nothing but 1, right? This is called unit, the unit. Because in the table it's A, right? Letter A. It's a letter A, right? In the numerator. However, this is the step. And if you're talking about unit step, it is 1 over S. Okay. With this particular input, what is the output? C of S just equals to R of S times G of S, which means your G of S is nothing but this 1 K over S plus A, right? So this is the output in frequency domain, in S domain, okay? Be very careful, okay? This is the frequency domain output signal, right? And then what we're gonna do is do the partial fraction on this guy so that we can find the C of T, right? So how to do this partial fraction? This one is easy, right? And I'm saving the middle step and directly present the result of the partial fraction. A constant divided by S and plus another constant divided by S plus A, right? Of course, the first constant is K over A. The second constant is negative K over A, right? Does it make sense? This is nothing but partial fraction. Okay, this step is partial fraction. So yes, this module remains to require the partial fraction. Okay. And from this partial fraction result, we can apply the inverse Laplace transform, right? So lowercase c of t equals to what? We need this table. And by observing this table, obviously, you can easily tell. You can tell this is a k over a minus a over a e to the negative a times t, right? And of course, if the handout is besides you, you can take a look. You can take a look at yourself, right? This is doing nothing but table. This is doing nothing but table. Any questions so far? A unit step response, we got it. We really do. A time domain function of time t. We really find it. Really find it. What's next is just what does the output curve look like? Looks like what? Right, remember? So, which means you're trying to see what does it look like. Lowercase c of t versus time t, right? What does it look like, right? So how to study this? So first of all, when t equals to 0, c of t equals what? And once t is approaching to infinity, c of t equals what? We study the starting point and ending point, right? We basically, let's figure out these 2 points, right? And then we can see the middle. So initial value, obviously this is t equals 0. This is nothing but initial value, right? Initial value. Finite t value. Then when t is approaching to infinity, then this output is what? Anyone know?
Well, all the transient terms, which is the e to the negative power, will go to 0.
No, I'm not asking for the value yet. So t equals 0, then c of t at this moment is the initial value, right? Then what's the definition for when t is approaching to the infinity? Then we'll see
final value.
Final value. Final value, okay. But actually it's nothing but steady state value. Steady state value. And here, no, I'm not asking for the value yet. Okay, we will see from there. Okay, so first understanding when t equals 0, the c output value is nothing but the initial value. When t is approaching to infinity, the output value is steady state value. Does it make sense? The time is already infinity. That definitely you have reached your steady state value, if there's one. The final value, that's fair too. The final value, that's fair too. This is a definition. So in future, we probably very often mentioning the initial value and steady state value, etc., etc. You understand what does it mean? In steady state value is what? C of t equals to infinity. How about that? So now, if this is clear, then go back to this result, obviously, to figure out what is the initial value of it. How to find the initial value of this guy? How? Of course, it's just substitute t equals 0, right? It's just a substitute t equals 0, right? And then if you substitute t equals 0, then what do you got? Yeah, no is right. 0. Does it make sense? Oh, t equals 0, then this guy equals what? 1. 1 times k over a. And then k over a minus k over a. 0. Initial value is 0. Then what's the final value? Yeah, Noah has already gave us that as well. K over a. Does it make sense? E to the negative a times infinity is equal to what? 0. Why is that? E to the negative t, what does it look like? I think you need to some algebra knowledge. What does it look like? That's right. It's going down. It's going down along the time approaching to infinity, right? So when t is equals to infinity, then this exponential function is equals to 0. So k over a minus 0 is equals to k over a. So this is how we got the initial and final value, or say steady state value. We're gonna do this a lot. Okay, we're gonna do this a lot. Okay, so being clear how we get the initial and steady state value. Okay. All right, next. After initial and the final value, then before reaching the steady state value, first order system has no oscillation. Okay, and this is the characteristic, one of the characteristics of first order system. There's no oscillation. What does it mean by oscillation? Oscillation means this oscillation. First order system doesn't have it. And no oscillation means what? Means no oscillation in transient, right? In transient. So how to plot this curve into the axis? Begin with 0 and ended by a constant which is k over a, right? So we're not sure when it's reaching that one. Okay, we don't need to, but basically it's just like this, right? At a certain time, it reached the steady state value and then stay at the steady state value forever, right? Makes sense. So this is just a rough curve, just a rough curve. Okay, but based on what we have now, we can only just reach here. Yeah, reach here. Okay. And of course, at certain moments, we don't need this guy. At about this moment, you're reaching the steady state. Before it, from beginning to up to this end, up to this time moment, it's transient, right? Transient. From then on, just steady state. Right? So be careful. The transient and steady state, obviously, very easy to tell which is which, right? If we're given the graph. So before reaching the steady state value, you have a transient. And this guy is, be very careful. This steady state was steady state value. Okay. A steady state value. Okay. Another thing is very easy to tell is what with different, of course, K and A values. The curves vary accordingly. How they vary? It's like this, okay? So roughly like this. You might have steady state like this. And the transient like this. And you might have something like this. What's the difference between these two? Both transient and steady states are different, right? Does it make sense? So the blue one, the steady state value is here. Steady state value 1. To the black one, you have steady state value here, SS2, right? And to the transient, you have these amount of transients for the blue and these amount of transients for black, right? So having different values for K and A, of course, you have different curves. Okay, so such kind of variation. Okay. It's not a surprise. Now let's learn something more specific. More specific. First order system. Performance specifications. This is where we're going to have calculations for. This is where we have calculations for. Okay, so how we conduct the calculation here. Okay? It's based on the definitions of everything. The first one we need to learn is called time constant. Time constant. Defined as letter T sub C. Okay? Time constant. I believe many of you already have some experience or at least heard of it before. And let's see. What does it mean by time constant? The time constant means the time, okay? It's not y-axis. It's obviously not y-axis value, but x-axis value. All right? Because we are talking about time. And the time it takes for the response, which is an output, to rise to how much? I think most of you guys remember this number, right? It's 63% of this steady state value. The time it takes for the response to rise to 63% of this steady state value. This is a definition for time constant. Next one is rise time. Rise time. T sub r. It's not surprised it's also a value along the x-axis, right? It's not y-axis value. Rise time means the time it takes for the response to go from 10% to 90% of its steady state value. Right. So how much time it takes for the output to rise from 10% to 90% of the steady state value. Okay. So here, 63% and 10%, 90%, they're all percent. Okay. So obviously, before knowing the specific value, you need to know the steady state value. And then you know the percentage, right? And the third one is settling time. Settling time. What does it mean by settling time? Is T sub s. Settling time is not very easy, not very difficult to understand, right? Just it takes how long for you to settle down to the steady state value, right? Then the definition here is the time it takes for the response to reach and stay within 2% of its steady state value. And how to interpret this reach and stay within 2% of steady state value? It means reach to how much percent of the steady state value. Once again, this is saying reach and stay within 2% of the steady state value. It means it reach how much? Very good. Okay, no is right. 98 to 102%. What does it mean? So you have a steady state here value, right? So what does it mean by reaching the 90% and 98% is about here, right? Let's say this is 98%. It's a little bit lower than the steady state. So from this 98 to the steady state, you have 2% here. You have another percent, 2% is above here. Right. This is the 102%. Obviously, steady state value is right in the middle. But since this is first order system, a first order system is what? Has no oscillation, right? No oscillation, what does it mean? Once you reach 98%, it can stay within the what? 98 to 100% of the steady state, right? It won't be exceeding the steady state. So in this first order system, we need to worry about the other 2% exceeding the steady state. No, in the first order system, we don't need to worry about it. But if there's an oscillation in output, you should. Okay, 98 to 102%. Okay. You reach 98%, and then after that, well, it definitely stay within that 2%. Okay. This is a definition for 3 specifications. So let's now just have examples. Now is the example time. Now is the example time. Okay. The first order system say has no zero. Oh, by the way, what does it mean by no zero? It means this. So this guy has what? One pole of what? Who is the pole of this guy? -8. Good. And how about 0? No 0, right? No 0 at all. Good. Good. Okay. The noise is falling very well. Okay, so this, however, first order system, of course, could have 0. Okay, that's possible. That's the second scenario we will see. Okay, but by here we just assume no 0, and then we will see what's the difference between having 0 and without 0. Okay. Unit step response is given, and then find one. What is the steady state value? Second, what is the time constant, Tc? Third, find the system transfer function. And I have posted the unit step response in the canvas. Let me show you. And if convenient, you can now just go to there to download it. Okay, it's module 4 and handouts. Can you see this guy here? Handouts module 4, and if you click it, and you can download this graph for your own use, right? For your own use, and it is just like this. Okay, like this. Module 4, example 1, the given step response, from where we can find the 3 things: steady state values, time constants, and the system transfer function. Okay. And to here, I'm gonna do this. I'm gonna just place this graph over here. I'm gonna do this. I have a printed version here. Printed version here. Let's see how to do this. So first of all, you need to understand the problem like this is actually not telling you the transfer function. Instead, is looking for the transfer function. So no transfer function. So we need to find what? Find question 1, the 2 answers by observing the given graph. Right? It's a reading graph. It's a reading. It's a reading problem. Right? So go to here and let's read this. Let's read this. What is the steady state value? Any answers from you guys? Just a simply reading. There's no trick. Okay, that's steady state value. What is it?
7.2.
7.2. Good. Good. I like that. I like that estimation. It's quite fair. It's nice that the steady state value is labeled at this side, this end. I mean, this side of y-axis. Remember one tip. If this steady state value is not labeled by this dashed line here, how you read the steady state value? Read this end, okay? Read this y-axis. Don't read from here, okay? It's not. It's less accurate. Does it make sense? So read from here is easier. It's obviously read from here is easier. Okay. So how to? I'm trying to. Yeah, it seems this point is what? 1/5 of this division, right? 1/5 of this division. This one division is what? 0.1. Does it make sense? This one division is one. It's just a 0.1. Right? So 1/5 is what? 0.02. Here is 0.02. Plus onto 0.7 is 0.72, right? Go back to here. Steady state value equals to 0.72, right? Keep reading. What is time constant? Well, first of all, what does it mean by time constant? The time takes for the time response to rise to 63% of steady state value. All right, we already have steady state value. So 0.72 times 63%. Right? We first of all need to know what value we are looking for. Right? It's 0.45, right? And 0.45 times, excuse me, at 0.45, what is the corresponding time moment, right? And then go back to here. And probably this is a little bit tricky, and you probably have to estimate. So 0.45, what is 0.45 here? It's here, right? It's 0.45 is here, right in the middle between the 0.4 and 0.5, right? And then what you need next is what? Is a ruler, right? It's a ruler. Make sure you are plot a horizontal line as flat as possible, of course. Intersecting with the curve by this time moment. And then what do you do? Go to the x-axis. There's another tip. Okay. This point is actually kind of right in the middle of the paper, or say along the y-axis, right? However, if this point is about here, where are you going to read? Read upper one, read upper x-axis. Okay, don't go down. Less accurate. For the same reason, remember? Read this side or this side, or reading this side or this side. It's up to where is closer. Does it make sense? Remember this tip. Okay? Remember this tip. Where is this? Is it close to? Okay, you read from there. Okay. Now is once again, it's time for you to estimate how much is this? How much is this? This have to admit this is a little bit hard to estimate, but any value you can have. What's the we already got it. This is 60% of the steady state value. Corresponding time is nothing but t sub c. So what this t sub c is equal to 0.12. 0.12 is fair. 0.12, in my opinion, is fair from Kevin. 0.12 is fair. Okay. Because from this is what? Right in the middle is what? 0.1, right? And this is about what? I would say is 1/3. So my estimation is actually 0.13. But if you gave me 0.12, I think it's fair too. It's a fair too. Of course, however, look at this moment. If you give me 0.15, I'm sorry, you're losing point. Does it make sense? Because 0.15 is supposed to be 3/4, right? 3/4 of the division. However, it's absolutely not 3/4. Absolutely not 3/4. It's kind of a little bit more than half of the division. So give me 0.12, 0.13 is fair.
I think we lost volume again.
Hello? Hello? Can you hear?
I can hear you now.
All right, good. I just learned, well, from IT people that just a refresh, they said sometimes they solve the problem. And where are we at? Guys, where are we at?
Number 3.
No, okay, the beginning of the number 3? Okay, so
Yeah.
so number 3, okay. So based on the steady state value and
Your screen share is not up anymore.
oh yeah, that's right. Thank you for reminding. Thank you for reminding here. So with steady state value and the time constant TC, we're gonna try to find the system transfer function. So the problem has already told us that there's no zero, right? So this is the function we can assume at the beginning, right? K over S plus A. We can assume this. And then these two are about output. So what do? We find output, right? We have done this already, but we can repeat it. Okay. Output equals input times the transfer function. Input is whom? Unit step is whom? The problem is telling you unit step, okay? Be very careful. It's telling you it's unit step. Who is it? 1 over S. Right? 1 over S times the transfer function, which is K over S plus A. Right? And then we're going to do the partial fraction. Right? Inverse Laplace transform C of t is equals to over A minus A over A times e to the negative A times t. Right? Now what? We know the steady state value is 0.72. What does it mean by steady state value? C of t equals what? Is 0.72. Equals what? Anyone remember? We just discussed. This is not
Infinity.
Infinity. Good. Infinity. Here we go. This is what? This is nothing but one equation, right? So you substitute t equals to infinity to here. So 0.72 times equals to k over a minus k over a times e to the negative infinity. This is nothing but equation, right? This is nothing but equation. One equation, how many unknowns? This is one equation, how many unknowns? How many?
2.
2. Exactly. One equation, 2 unknowns. Can do nothing. But it's fine. We have a second here, 0.45 here. We have 0.45 here. So what do you do? C of t equals to tc, which is what? 0.13 is equals to what? 0.45. Right? We already got these from here. This is going to give you second equation. Then what is it? K over a minus k over a times e to the negative 0.45 times a. I'm sorry, negative 0.13 times A. Does it make sense? Any questions? All right, if this is clear, then go ahead to solve them. I mean, 2 equations, 2 unknowns. Very, very straightforward. Come up with what? K and A. That's what we need. With K and A, the transfer function is solved. Give you guys 2 minutes to solve this K and A values. 2 minutes. Go ahead. All right, and I already see Noah got the correct answer, so I just present it here. Okay. 7.5-ish and 5.5-ish. So system transfer function is 7.5 s plus 5.5.
So I'm kind of questioning why is it that it's 1 over s and not like some constant over s? Because couldn't the input signal, if it was constant, be instead of 1, couldn't it be like 20? Or is that
The problem, this particular problem is telling you is unit step.
so it's singular, meaning that the source itself has to be just of 1, right?
Yeah, unit step means unit step.
So 1 unit, and that's why it's 1 over s.
Yes.
Okay.
A equals to a 1. Then.
Would they
A
ever go like 4 unit step, where it would be 4?
No. No. That way is tell you. That way gonna tell you like this. They tell you the input is 4 over s. They're gonna tell you, or say the unit input is 4 over s. They call it unit. Call it step input as 4 over s. Step input, without mentioning the unit.
Oh, okay. So this is basically implying that we're putting some sort of signal with a 1 value, and since our steady state value is less than that, there has to be some sort of loss, voltage division, right? Since it's a first order system.
Why is that?
Because our steady state value isn't equaling the input step source of 1.
Well, not necessarily equal to. And this scenario is kind of like this scenario. You're not having probably you don't have any feedback. You just have plant itself. No feedback, no controller either. You give an input, it gave you output. output which is not necessarily equals to input. You don't have even a feedback. You have no control either. Right? We just study this system for performance. Does it make some sense now?
Okay, yeah.
Because you don't have to, well, output equals to input. No, well, not necessary. Assuming we're just studying a system without any controlling, without any feedback yet, well, right? It's just this system itself. Right? And no one is saying this system is good. Okay, no one's saying that. We're just studying this system. No one's saying it's perfect system and blah blah blah. No, it's not perfect yet. Any questions regarding this example one? This is given the graph. From the graph, you can tell some information and further to determine the system transfer function, right? This is one way. Okay. We can have more examples for the other way around. Example 2. Given a system transfer function like this. Then find also unit step response TC, TR, and TS. Right. This is the other way around. You can tell, right? And it says given the system transfer function, I'm looking for the three T's. Right. So once again, same idea. You're talking about the output. Okay, we got half the output. C of S equals to R of S times G of S. Right? And then unit step, okay, unit step input times, right? And from here, you're gonna do the partial fraction by doing this, right? And then you find the two coefficients in the numerators respectively. Right? From midterm 1, I noticed seems that you guys obviously learned the how to find the coefficients. You guys have your own method, you have your own way from other math class. However, some of those methods, well, doesn't work very well to me. It seems you can't find the correct value. Anyways, we leave that for later review lecture. Here, let me repeat my method once again. Okay, I hope it makes sense to you. I'm assuming K1 and K2 here, and therefore, what I'm seeing here is S times 50 is equal to K1 times 50 plus K2S. So in the numerator, we have the K1 plus K2S plus 50 K1, right? Denominator remains same. So we immediately come up with two equations. K1 plus K2 equals what? 0. There's no S term. 100 only. Constant term, right? So no S term. Over 50 K2 is equal to 100, right? So from here, you can tell K1 and K2 value. K2 is 2. K1 is -2 then. Right? Therefore, C of S equals to -2. It's K2 is 2. Let me see. K2 is 2.
Should be K1, not K2 as the positive 2.
That's right. Like this. How about this? Is it better? Right? But this is a partial fraction. This is my way to do it. So you guys have some sort of even derivative or something, which is not necessarily wrong. However, well, in the exam seems didn't work very well. Anyways, from here we got the inverse Laplace transform to get lower c of t, and then therefore you got the 2 minus 2 e to the negative 50t. This is the output. We got output. From output, as well as the 3t's definitions, we can find their values. Right? First of all, TC. TC means what? When time is at TC, your output reached 63% of the steady state value. Right? And from here, before that, of course, we can find the C of steady state value. Steady state value is equals to what? 2, right? Of course, you can also find the initial value, which is 0. Does everything make sense so far? Infinity, substitute into here, you got 2 as that is the value. 0, go to here, you find initial value as 0. Right? The time constant equals 63% times the steady state value, which is right. And then T equals TC is what? 2 times 2 minus 2 times e to the negative 50 TC. It just equals to 63% times 2. From here, we got TC value. Similarly, to find the TR, what we do? If you check your notes, the TR definition is the time it takes for the response to go from 10% to 90%. So what can we do is to find 2 time moments. One is for 10%, the other is for 90%. And the difference between these two is the TR. Does this make sense? So what do we do? C of equals to 10% time moment. Going to be 10% times steady state. From here, we have 2 minus 2 times the negative 50. 10% equals to 10% times 2. On the other hand, when t equals to 90% of time moment, you really have 90% of the output steady state. 2 minus 2 times e to the negative 50 times t 90% is equals to really 90% of the steady state value. And respectively, you find t 10% and t 90%. Both are one equation, one unknown. At last, of course, equals what? Time difference between these two is t right. Is Does it make sense? Does the idea make sense? All right, thank you, Noah. Any questions, others? The rest thing is algebra, but I'm presenting the answer here for you to check and make sure you got the make sure you got the right answer. Any questions? All right, I think that's all for today, and I'm leaving the TS for you to do after the class. Following the same idea shouldn't be a problem. And what you're expecting about the TS? You don't know the correct answer, however, you can have a guess, right? Is a reasonable value, or say the range of the value the TS supposed to be fall into. Any idea? You can easily guess, right? You can easily guess. Well, what is the reasonable range for TS value? Any idea? Any thoughts about TS?
It should be a bit bigger than that 90% one that we already figured out.
Oh, very good. Very nice. Very nice. Very nice. Kevin's right. Okay. Because TS, according to the definition, is what? It's supposed to be the time it takes to reach 98%. You know the 90% to reach 90% is about 46 milliseconds, right? Reach further, 98%. You need to take a little bit more time. You need to take more time, right? Maybe not a little, but it should take more time. And of course, also because the first order system output has no oscillation. It can only go up, right? It won't fall down. Yep, so it should be higher than 46 milliseconds. All right, I think that's all for today, and thank you for attending today's lecture. And my office hour is right after, so you can find me from the Teams if any questions. Otherwise, talk to you guys on Monday. Bye now.